Good day, everyone. My name is Dr. Oluwafemi George from the Department of Systems Engineering, University of Lagos. Today, we'll be continuing our lectures on operational methods one, specifically on periodic function, average of periodic function, Fourier series, and everything that has to do with that. So far, we've looked at a periodic function. We give this graph. We said the periodic function is a function that repeats itself at regular interval. And we also give the average and root mean square of a function over an interval a comma b. We define average of a function as y bar equals 1 over b minus a integral from a to b y dx, and the root mean squared as y bar which is equal to the square root integral from a to b y squared dx all over b minus a. And we also give series of examples. So the first one, if f of x equals x squared, f of x equals 2 minus x in the range of 0 less than x less than 1 and 1 less than x less than 2. And we are asked to sketch the graph of y equals f of x for minus 6 less than x less than 6 if f of x is periodic of period 2, f of x is an even function and periodic of period 4, and lastly, if f of x is an odd function and periodic of period 4. Also, we will give this question, we have to find to show that f of x is an even function. That is, if f of x is equal to 4x minus 4x squared in the interval of 0 less than x and x less than 1, and f of x is periodic of period 1. And lastly, we are to sketch f of x over the interval minus 2 pi less than x and x less than 2 pi, given that f of x is equal to x for 0 less than x less than pi over 4, and f of x equals sine x for pi over 4 less than x and x less than pi over 2. So the solution, the sketch for these questions are also already provided. So if you miss any of our lectures, previous lectures, you can just click on these two links to watch the full video on that. Very briefly in this video, I'm going to take us through the rules in finding the average of periodic functions. Most periodic functions can be expressed as the sum of sine and cosine terms, that is, the representations of mechanical vibrations, electric and magnetic fields, and so on. So we need to know the average of such terms, their RMS, and other properties. So we therefore shall derive general rules for the average and RMS of sine and cosine and their products over their corresponding periodic and multiples of such periodic interval. So as the first rule, so if omega is greater than 0 and p is equal to 2 pi over omega, then the average of cosine of omega x plus phi or sine of omega x plus phi is 0 for the interval 0 comma p. So, and the proof is as shown. So if we let y1 is equal to cos of omega x plus phi in the interval 0 less than x less than p, then we can write y1 bar p equals to the integral from 0 to p cos of omega x plus phi dx. So if we integrate cos of omega x plus phi, then we have sine of omega x plus phi, then we can introduce the interval from 0 to p, then eventually we have the expression as sine of 2 pi plus phi minus sine of phi, and this gives us 0. So we have that our y1 bar is equal to 0. So similarly, if we let our y2 equals sine of omega x plus phi, then we can also show that y2 bar equals to 0. So as you can see here, so if we let y2 equals sine of omega x plus phi, comma, then we can show that our y2 bar p is equal to the integral moving from 0 to p of sine of omega x plus phi ds, which is the same as, if we integrate sine of omega x plus phi, we have minus cos of omega x plus phi plus phi in the interval 0 p. So, and this leads to 0. So that is, we have that y2 bar is equal to 0. So rule number 2, if omega 1 and omega 2 are distinct, that is, omega 1 is not equal to omega 2 and p is the interval period, a common multiple of the wavelength corresponding to omega 1 and omega 2, then the average of the product of the sine or cosine of omega 1x plus phi 1 with the sine or cosine of omega 2x plus phi 2 for the interval 0, p is 0. That is, if we let beta 1 equals omega 1x plus phi 1 and beta 2 equal omega 2x plus phi 2, then we have that a 1 over p integral 0 to p sine of beta 1 sine of beta 2 dx equals to 0. B 1 over p integral from 0 to p cos of beta 1 cos of beta 2 dx equals to 0. C 1 over p integral from 0 to p sine of beta 1 cos of beta 2 dx equals to 0. D 1 over p integral 0 to p cos of beta 1 sine of beta 2 dx equals to 0 also, where p is equal to 2 pi n1 over omega 1, which is equal to 2 pi n2 over omega 2, and n1 is not equals to n2 since omega 1 is not also equals to omega. Now we want to prove that 1 over p integral from 0 to p sine beta 1 sine beta 2 dx equals to 0. That is 1 over p integral from 0 to p sine beta 1 sine beta 2 dx equals to 0. If we recall, we say that 2 sine beta 1 sine beta 2 is equal to cos beta 1 minus beta 2 minus cos beta 1 plus beta 2. So we can therefore write the integral from 0 to p sine beta 1 sine beta 2 dx as equal to 1 over 2 the integral from 0 to p cos of beta 1 minus beta 2 minus cos of beta 1 plus beta 2 dx. So if we also substitute beta 1 as omega 1x plus phi 1, also beta 2 as omega 2x plus phi 2 into this equation, then we can write that 1 over 2 the integral from 0 to p cos omega 1 minus omega 2 x plus phi 1 minus phi 2 minus cos of omega 1 plus omega 2 x plus phi 1 plus phi 2. And of course, the x. So this is same as 1 over 2 sine omega 1 minus omega 2 x plus omega 1 minus omega 2 over omega 1 minus omega 2 minus sine omega 1 plus omega 2 of x plus phi 1 plus phi of 2 over omega 1 plus omega 2. Then we integrate the interval 0 to p. So if we let omega 1 equals 2 pi n1 over p, also omega 2 as 2 pi n2 over p, 2 pi n2p over p, and substitute back into the expression, we have p over 2 into sine of 2 pi into n1 minus n2 x over p plus phi 1 minus phi 2 over 2 pi n1 minus n2 minus sine into 2 pi of n1 plus n2 x over p plus phi 1 plus phi 2 over 2 pi n1 plus n2 the interval 0 to p. Now, if we let phi 1 minus phi 2 equals to theta minus phi 1 plus phi 2 equals theta plus. Also, if we let n1 minus n2 equals m, and n1 plus n2 equals m bar, we can write that p over 2 into sine of 2 pi m plus theta minus sine of theta minus over 2 pi into n1 minus n2 minus p over 2 into sine of 2 pi m bar plus theta plus minus sine theta plus over 2 pi n1 plus n2. So if we apply sine of a plus b equals sine a cos b plus cos a sine b. So let's go through it together. So applying sine of a plus b equals sine a cos b plus cos a sine b. So we can write that sine of 2 pi m plus theta minus sine theta minus as sine of 2 pi m cos theta minus plus cos 2 pi m sine theta minus sine theta minus. So for integer m, that is m equals 1, 2, 3, and so on. So for m equals 1, 2, 3, and so on. So we see that sine of 2 pi gives us 0. Same thing with sine of 4 pi, sine of 6 pi, 8 pi, and so on. So this expression gives us 0 automatically. So in the same vein, for m equals 1, 2, 3, then we know that the cos of 2 pi gives us 1. So this gives us 1. Cos of 2 pi gives us 1. Cos of 4 pi gives us 1. So we can write that the sine of 2 pi m plus theta minus sine theta minus is equal to 0 plus sine of theta minus sine of theta minus, and this gives us 0. So in the same vein, I say similarly, the sine of 2 pi m, sine of 2 pi m bar plus theta plus minus sine theta plus the same as sine 2 pi m bar cos theta plus cos of 2 pi m bar sine theta plus minus sine theta plus minus sine theta plus. So the same way for m bar equals 1 2 4 m bar equals 1 2 3 and so on, we can write that sine of 2 pi m bar plus theta plus minus sine of theta plus is equal to 0. Of course, this one will have given us 0, and this expression will have given us 1. So it will be 0 plus sine theta plus minus sine theta plus, and this gives us 0. So hence the proof, hence you can write that, hence we have shown that 1 over p integral from 0 to p of sine beta 1 sine beta 2 dx equals to 0. And this comes to the end of the first proof